There is a rule.
Yeah, okay, so it's not bullshit.
There's no bullshit. Let's go. We're gonna take a photo of this.
I just want to try it.
This is it?
Yeah. Which one? Okay. Is it comfy? Yes, it is. Oh, this is awesome. Yeah, let's see here. This is way better. See, let's see.
Yeah.
This is fun. It's so comfy.
I can imagine.
You have to try. Okay. This is more comfy than this one. That's five. What is this? 18. No.
This is one.
Yeah?
This is 5.
Look how a chair can change your
And then this is 7.
Yeah.
Okay. And this is 15.
I mean, this is not applicable anymore.
You did. Try one.
No, I still don't get it.
Me neither.
We took way too long yesterday, so there's no rush.
Yeah, maybe.
Okay. I think we give it another 5 minutes or so.
Is that right? Okay, so here we
No, I
go.
think we wait maybe for Martin and
Okay, but I can get this going, right? And then eventually, if you project it, it'll be
yeah, if you want, I can switch over if you want to start up, or you let me know, please.
let's see where we are. Oh, this was moved again.
If I survive by the end of the summer school without getting blind, that would be awesome.
That happened.
It just happened a few days before the summer school.
What do you do?
I just sat on my computer.
If you need a hand with anything,
Making noise.
So,
Yeah, so if I don't get blind, that would be great.
At least you got here.
At one point, I felt that my eyes was feeling something inside.
start recording.
It didn't put that in my eye now, but it was not.
No, it's not. So, let it start. So, okay.
You were there, we were playing the game last night, you were not there, no? Inside the Okay, folks. Number games.
I think so.
All right, so we have come to the ultimate course, the final speaker, Andreas Mandelis from the University of Toronto, has been working in this area for a very long time, and as is the tradition so far, I'm not going to introduce him because I guess you will introduce yourself to some extent, so thank you, Andreas.
Okay. So, good afternoon, everyone. You spend the whole morning listening to a lecture about photoacoustics. Well, there's going to be some more of that because there are many different areas of photoacoustics where the science and the technology has been moving, And what I'm planning to do is to discuss essentially some of what we do. And the area that we have introduced and been developing is frequency domain for acoustics. And that also goes from a very simple principle. It has challenges like Matt was talking about in the morning, but it also has many advantages. So if you look at optical coherence tomography, it started out as a time domain technology, and then eventually it ended up being frequency domain, and nowadays frequency domain is really the dominant form of optical coherence tomography. What frequency domain has a major advantage is phase. You have a phase, and the phase has special characteristics. I think Matt was talking about it a little bit in the morning, but the other advantage that you have is that in frequency domain, you can manipulate parameters. You're working with the spectrum, so you can do spectral engineering, something that you cannot do in the time domain, because time domain is a laser, it's an optical hammer, it goes bang, bang, bang. There's not much you can do about it. Every 1/10 of a second, you're going to get a pulse out. You can play a little bit with the spectrum, but there's not so much, for instance, adjusting that to the transfer function of the transducer. A lot of these things you can do in the frequency domain. And I'll show you some of the other advantages where the frequency domain for acoustics is not just me too, but it has specific advantages. Another thing that I wanted you to know is that basically what Matt presented in the morning was frequency domain as per biomedical. Photoacoustics started out 30, 40 years ago, the modern day of photoacoustics, which was in the 1970s, when he was talking about Oraevsky and Nihon Wan. These people were students of other people who were photoacousticers, so the primary photoacoustics workers or researchers that started the field in the 1970s, they restarted it because the field had been started by, after Alexander Graham Bell, there were a number of Russians who were actually working on photoacoustics in the 1930s and 40s, and then there was a big gap, and then finally we ended up in the 70s. So who are the people? They mostly came from Bell Labs. Parker was the first one who started the whole idea of modulated light generating sound. Alan Rosenzweig was also working at Bell Labs at the time. He was working with Parker. Eventually, he owned the idea for acoustics. He as the father of acoustics, but in fact, it could have been like the son-in-law of acoustics. I'm not exactly sure. But Parker came in with the first idea. And then you had some other people, Kumar Patel. Kumar Patel was also working at Bell Labs, and he was actually one of the generators of gas phase for acoustics. Because again, one of the advantages of acoustics is that you have a huge dynamic range. Unless there's an absorption, there's no signal. So if you can tune to an absorption of a gas, and then you can get something away from a baseline, that gives you a huge dynamic range. That's where photoacoustics wins. It wins at early stage diagnostics, and that has carried out all the way to the biomedical field. And then it's Andy Tam, and Tam was working for Bell Labs to begin with himself, and then he ended up going to IBM in California, and he was also central in generating essentially gas phase and solid state photoacoustics. These are the photoacoustics people. Their students then eventually they started making the gap between the conventional photoacoustics, and the conventional photoacoustics was a gas cell with a microphone in there. But you're working in the audio regime. You're working at 100 hertz, 200 hertz, 20 hertz. So the acoustic wave was a carrier. All you're really doing is you're modulating the heat, the thermal boundary layer, and that was going to the microphone. So you're getting things like optical absorption spectroscopy, you're getting thermal parameters. So because photoacoustics was not working in the high frequency regime where the thermoelastic effects become obvious, where the speed of sound comes into play, was way below the speed of sound. All these other aspects, there's some biological applications, there's some solid state applications, gas phase and liquid phase, photobiology came in, all of these things came in early. And then eventually you ended up having so the whole thing was diffusion waves. That is, you were basically monitoring diffusion, thermal diffusion, with an acoustic carrier. So the whole idea of diffusion wave came in, which is something that I kind of honed onto because I did my PhD in photoacoustics in 1979, way before these fields, the biomedical field, started. So the whole thing, you can see the connection, or the disconnect for that matter, because at the time, most of the information, most of the studies were done in a non-contact, non-destructive mode with a microphone here. Some other people came later and put photothermal, so part of what I'm going to talk today, the third part is photothermal diagnostics, photothermal imaging, as opposed to photoacoustics. And then, in the late 1900s, Orevsky came up, who was a graduate student at the time at Washington or Oregon, I forget which one it was, but he was working with Steve Jacques. So Jacques was a biomedical optics, a biophotonics man. Orevsky was aware of photoacoustics. He put essentially the light and the acoustic transducer together, the ultrasonic transducer. So that being the case, you have a phenomenon in this field that basically has two branches. The classical photoacoustic branch, which did not utilize much of a transducer. I mean, some people tried in the 1970s to study optoelectronic phenomena, which is one of the things that we do. That's why I put that on the board, because you can study diffusion waves made by electronic carriers. The time scales are on the order of milliseconds, microseconds. So in order to see those, because carriers move much faster than heat, in order to see those, you have to have a transducer, because the microphone could not do it. Microphones go maybe up to 4 kilohertz. You also have mechanical choppers of the light, so they cannot go. People were sticking transducers to the back of the semiconductor wafer. People won't buy that. Anybody in the semiconductor and optoelectronics or microelectronics industry, if you stick anything to the wafer, they don't like it. So it worked for a while, and then it died. And it came out of 20 years or so in the late 1990s, maybe 2000, where suddenly we find out that this configuration of light input, water interface for acoustic impedance, matching like Matt was talking in the morning, and the transducer, the ultrasonic transducer, was new. And it was acceptable in medical ultrasound, so then we go one step further and we put a light into this. And that's how this field started. But interestingly, these two fields remained apart, because for biomedical photoacoustics, what you really need is a light source and an ultrasonic transducer, or an array. Whereas for all the rest of the photoacoustics, what you do is you need either a microphone or you need the laser beam and thermal phenomena to be able to study that. So the two communities have remained relatively apart. I've been trying hard, one of the few people who actually has his legs in both communities. And so I'm trying to get them together again, and there are indications, because there are ways that the biomedical group can learn tricks from the actual original photoacoustics, and some of these things I'm going to bring to you today. So anyway, this was by the way of the history as per Mandelis. And what I wanted to show you is this is part of what we do at the University of Toronto. We have a center for diffusion wave and photoacoustic technologies, and we look at things like diffusion. Diffusion is thermal diffusion, it is electronic diffusion, and the photoacoustic field, well, it happens to be one of those diffusion waves where you're not at the diffusion limit. You want to be in the adiabatic limit, so that when you get a photoacoustic image, the ultrasonic image is going to be a good replica of the optical image. So you don't want to have the thermal diffusion out, but you can use thermal diffusion. You can use in many different ways. So we've been working with things like metals and coatings, non-destructive testing of metals and coatings, where you study properties and, most importantly, subsurface defects. So non-destructive testing is very important, and then I regard biomedical photoacoustics as non-destructive testing for tissue. You're looking for the defect below the surface, except you deal with tissue instead of a piece of metal or a piece of some other material. And then we also look at things like optoelectronic materials and microelectronic, because you have electronic motion, that's diffusion. So you look at carriers, electronic carriers moving to materials, good materials, bad materials. These electrons, they move, they fall into electronic states, they produce photons. So the goodness of the material depends very much on the receptor, which could be a photonic receptor. Then we also have things like we make thermal wave and sensors. Okay, so there is an entire area of Fourier transform infrared photoacoustic spectroscopy, which is very wideband in the infrared. So you can just put the optical source, very wideband optical source, and you can get spectra very fast. So people have been working with analytical techniques, Fourier transform infrared spectroscopy, they would be aware of. This is a part of an analytical lab, but it's also part of photoacoustics, because again, what Photoacoustics does, it gives essentially a very, very low baseline, very high dynamic range. We have been working with, all of these are optoelectronic. We have essentially companies we work with. In Canada, you cannot really get money from anyone unless there is a company that says how beautiful this work that this person is doing is, and we could use it for something. And then the federal government comes up and says, yes, there is money here. You compete, you write a proposal, and you get your money. So a lot of that is really associated with companies. I have two companies that I have started. One of them is Quantum Dental Technologies. Why? Because you use diffusion waves in dental applications. I'll show you some of those today. And we also have a second company, Diffusion Wave Diagnostic Technologies, which is mostly for non-destructive testing of things like automotive parts, aerospace parts, materials, and eventually biomedical, as you're sort of generating this technology. The Biophotonics takes advantage, or the basic physics behind it is diffuse photon density waves, so it's exactly what Dave Boas was talking about yesterday. And in this particular case, we have been developing frequency domain because, again, it has advantages. There are some disadvantages, but advantages, and today I'm here to tell you what is the good things about it. I'm also going to let you know what the disadvantages are. Now, so from the biomedical point of view, we ended up with several kinds of application lines in our research center. One of them generating a non-invasive blood glucose biosensor technologies using photothermal detection. And we're working actually with Pranalytica. Pranalytica is Kumar Patel's company. He makes quantum cascade lasers. So we've been working with him to monitor, to have essentially laser beams identifying the state of your blood, whether or not there is glucose in your blood through the skin without having to prickle the finger and get a drop of blood and the things that we know about diabetic problems. Then we also have an active program on the photoacoustic diagnostics of bone osteoporosis and photothermal, the reason being that when it comes down to hard tissue, hard scattering tissue, soft tissue scatters light. But ultrasound pretty much does not care about the scattering characteristics. But when it comes down to hard tissue, ultrasound scatters as much as light. So we have maybe a couple of millimeters, 3 millimeters penetration depth in the thing like in a piece of material like a bone. In that case, photothermal becomes really competitive because heat does not scatter. So you can start using photothermal imaging instead of photoacoustic imaging. And there are some advantages to that. And I'll get to that on the third part of my talk. Big advantages in terms of the technology that's available for imaging. And then we have an active program in a catheter generation, which is something that Mark was studying in the morning, that is generating frequency domain catheters for intravascular disease. And we're working with a hospital in Toronto, Sunnybrook Hospital, and Calibri Technologies, who will be marketing this kind of an endoscopy device. And the most recent, perhaps there's also photoacoustic radar imaging. So what we do, what frequency domain is, we just borrow ideas and concepts from the radar science, because we do need to have three-dimensionality. We need to have depth profilometry, and frequency domain needs multi-frequency in order to be able to go there. And another project that we had recently that's very nice is to look at a blood alcohol biosensor in Toronto. In Canada in general, there's a very strict, culture. Maybe it comes back from this part of the world where they really want to know how much alcohol you have in your blood, especially around Christmas time when everybody goes out and they drink. And then we have a program that's called the RIGHT program. And the RIGHT program is the police hiding under bridges, and as your car goes by, then they stop you and they want to take a breathalyzer test, and you could have some problems with that. So the whole idea here is to just get a non-invasive, non-contact blood alcohol biosensor so that people can tell what your blood alcohol content is essentially just by monitoring the laser beam and photothermal detection. So there's a number of these things. However, the first part of my presentation, this is just to make people familiar with the spectrum of the kinds of things that we do. The first part I'll be talking about is the introduction of frequency domain photoacoustics, the biophotoacoustic radar or sonar, and give information about instrumentation, signal processing principles, and some comparison with pulse laser photoacoustics, so we can see advantages and disadvantages. By the way, anybody who has a question, you better ask it at the time when the slide is on, because the slide is gone after that and people will have to chase it back. So it'll be very nice to get this question. I'll be very happy to answer questions from people. So I've given some relevant literature here. As I said, we started the field of frequency domain for acoustics, so most of the applications are from my group. Recently, there has been more sort of mobility in generating more frequency domain technologies in the field of photoacoustics. As Matt pointed out in the morning, a very simple design. I'm very grateful that he presented all of the background here, because I don't need to present much of that. The major advantage of photoacoustics is that it has a compromise, a marriage, a happy marriage between optics and ultrasound. So optics is suffering from scattering effects, not very high penetration. For acoustic, the ultrasound has low contrast but much higher penetration. You put the two of them together and you have a high contrast and less scattering, that is more penetration. And also finally, because you use waves, you use light, you can get molecular imaging. You can get things that you cannot get from ultrasound. Ultrasound is a mechanical wave. It reflects only from interfaces, when the density and or the speed of sound is different from one region to the next, then you get reflection. So you get, ultrasound is very good at giving you regions. You see a region of something. You can identify some tissues. You can identify essentially shapes, and then what the shape is made of, what is the content of the shape. This is something that photoacoustics will be able. The photoacoustics basically puts a blood in the position where the ultrasound is giving you the shape. It is not very good at giving you geometry, but it gives you things like blood. And we have seen some of those images in the morning where you see a very nice ultrasonic image, and then on top of that there are a few blotches of blood or some other characteristics that are due to absorption of the light. So, if you look at the signal generation physics, it's relatively straightforward. I said relatively, because you have light diffusion in the medium, so it is scattering as it moves forward. And but then you have what I call photothermoacoustic, because there's always a thermal interface. It's just like we don't call it that way because we're in the adiabatic domain or regime, time regime. That means you have to be fast enough to get in and out, which means that heat does not have enough time to diffuse. So, but heat is there, and heat is the generator of thermoelasticity. So you're really looking in the sort of megahertz range, in the microsecond domain, and that is what will combine these two together, because the light, of course, is much faster, so it's instantaneous as far as we go. And you have the acoustic wave propagation and an ultrasonic transducer somewhere that has a transfer function and some sensitivity. So this is again where the frequency domain becomes interesting, because you can tailor your spectrum to best match the ultrasonic transducer. Now, going back to that historical development, just one slide for that. As we mentioned in the morning, Alexander Graham Bell was the father of modern day photoacoustics in general in the 1880s and 1890s. He generated the photophone, the thermophone. The point was that he became aware of the fact that if you have light absorbed by somewhere or interacting with something, then there's sound coming out. He did not understand what the conversion factor was, how you convert from light to sound. But nonetheless, he was the first one to do it, and in fact, himself and people later, they claim things like you can listen to the clouds, because again, as the cloud goes by, then you have sound coming, and then another cloud goes by, and then there's silence and then there's sound, so you can create sound from light. So the laser, the advent of the laser in the 1960s was extremely important, because that's when we started having high intensity sources. Photoacoustics is essentially a very sensitive kind of a phenomenon. You need a lot of optical power in there. So with the lamps that existed before, it was not a great. People started doing some work, broadband work, but then they kind of stopped for a while because they did all they could do. But then when the laser appeared, suddenly you have a strong source. So photoacoustics again came to the fore. And you ended up with two different characteristics. I mean, the laser can be a pulse laser, it can be a CW laser, it could be modulated. So if you look at these, then eventually you had these two, and then one can add more things. Instead of having just a simple modulation, you modulate the intensity of the light. How do you do it? Well, you can actually use a chopper, a mechanical chopper, off-on, but that again is going to take you maybe up to 3 or 4 kilohertz, so it is not very good for biomedical applications and imaging. Or you can actually, in today's world, you can have laser diodes, you can modulate the current of the laser diode, so now you really are looking for high frequencies. So, one of the major problems in technology in actually identifying and implementing frequency domain photoacoustics is that it goes in tight pace with the development of high frequency, high peak power semiconductor diode lasers. So we are looking at, let's say, megahertz modulation at maybe 10 watt peak power. This is where we stand right now. So there is one company in the world that makes it, and there's another company that makes drivers for that nowadays. So when you put them together, you have a successful frequency domain operation, but that is a major factor. And those lasers now, they're not very expensive. We're not talking about those huge, large lasers that we have for pulse photoacoustics. Today we heard that there's a Russian company that makes new lasers, maybe in the kilohertz regime, but what we're looking for is to be able to get a high signal-to-noise ratio, higher than we can get with conventional photoacoustics. And the way to do that is by scanning the frequencies. So we still do not have the ideal laser. The ideal laser is one whose frequency could be changed externally, could be controlled and changed externally, and the range of that frequency suite would be in the megahertz. That we don't have yet, so I have to make it. We make it through control of the current, but then again, sometimes we have problems with the high current. So at the same time, the coding, the kind of modulation you do matters, because that can optimize the signal. One of the major disadvantages of frequency domain is that the signal is relatively low. It's not like you don't have a powerful pulse that goes in, I don't know, maybe it would be gigawatt pulse coming in for 10 nanoseconds. You don't have that. So you really need to look at the frequency domain and say, I'm going to have over the entire duration of the illumination of the material, there's going to be enough energy going in there to generate a signal. So signal-to-noise ratio matters, and this is where you pay the price. You have to be more sophisticated than with a pulse laser. So one of the sophistication areas is using coded optical excitation, and then, importantly, the idea of the radar or sonar. So to put it in, a few points here. What is the frequency domain for acoustic imaging using the CW laser source? Well, it has some advantages. Those lasers are basically inexpensive and compact diodes that can be used for acoustic wave generation. Instead of buying the $70,000 pulse laser, you have the $3,000 or $4,000 laser diode. That's small, not this big. The other thing is you can do shaping of the photoacoustic response through specific intensity modulation patterns, so you can do, as I said, waveform engineering. This is a methodology, this is a terminology that we coined that exactly goes to the heart of it. You can optimize your signal by looking at what the components are and going in and making it into a viable kind of a signal generation process. And then the high repetition rate then could go higher than 1 kilohertz, or as we know that pulse lasers are maybe about 10 hertz. In your dim mag laser, 10 hertz, so the speed with which you're generating an image is important. So we have not gotten yet to the real-time imaging, but 1 kilohertz versus 10 hertz or even 10 kilohertz is 3 orders of magnitude better. That means that the image generation process is becoming a lot more feasible. And then most importantly, it's frequency domain. And today's ultrasonic imagers are frequency domain animals. We talk about pitch, catch, and so on, central frequency, a frequency range. So most of the software is written for frequency domain. This is what your ultrasonic imagers are. This is also frequency domain. So it's easy to integrate the software of a photoacoustic system into an existing imager, ultrasonic imager, without having to reinvent the wheel. We're not going to reinvent ultrasonics. Ultrasonic imagers exist. And their imagers, what you need is an imager that has actually both a medical interface that is a medical doctor can use, but also a research interface. So a graduate student or a postdoc, or even an undergraduate eventually, can use to input the software and have both the ultrasound and the photoacoustic at the same time, which is what we mentioned, or what Maros mentioned in the morning as co-registration, signal co-registration. You put the ultrasound, you put the photoacoustic image together. So the disadvantages, signal to noise ratio is very low. So you have to do work for that. You have to generate the conditions under which this can work. And the high spatial resolution cannot be achieved with long periodic signals. So you really need to go into the megahertz range, which is what I told you before, that you need to have lasers that are modulatable in the high frequency range. Now, the solution here is to use photoacoustic correlation imaging with coded optical excitation. What happens is, think about why radar is a natural technology for that. Why was radar invented in the first place? Because people had those really long pulsed sources in the past, ultrasonic sources, electromagnetic sources. You really wanted to have a compact system that would generate the equivalent of a pulse system. So in order to do that, you had to have two conditions, at least in the field of ultrasound. And that is, one of them, it has to be that you have a match filtering, that is, you have a filter that matches the waveform that comes in, and the other one is pulse compression. That is, you take all of the individual waves that come in and you move the phase so that all of them essentially appear at the same time. So then the pulse compression gives you a peak, and the match filtering eventually is the one that is going to give you the high signal to noise ratio. Yes? Oh, I thought you raised your hand. Oh, you peak, right, you have a peak. Right. You're looking for that damn peak.
Going down next time. Peaks down there.
What goes up must come down. Okay. So what are the advantages? So I showed you the major disadvantages of low signal to noise ratio if you just simply generate an acoustic ripple, an optical ripple, and then you can generate an acoustic signal. Look at this beautiful or ugly kind of impulse response. This is actually the result of a pulse laser that has generated a photoacoustic signal. And what I usually see is the impulse response. That is, if I have a very fast pulse coming in, a delta function pulse, is essentially the physics behind it is, first of all, there's a compression. So the acoustic wave that's generated is compressing the material, and then there is a rarefaction that comes after. So what happens is I get a compression, I get a peak up here, and then I get a dip, and then back again. So these are N-shaped pulses. This is what you get with a pulse laser. And that would be great if you could get that without anything else. But at the same time, you have important adverse factors. And one of them is ringing. The transducers ring as well. So you have a whole lot of things here happening. The baseline is moving. Sometimes you have direct, that was observed early on with photoacoustics when people were using pulsed laser photoacoustics in the 1970s. Some of the first experiments that were done, that is, some of the stray photons go to the transducer and they produce a signal of their own. So in order to avoid that, some of the first people that were working with photoacoustics, with pulse laser photoacoustics, they put a mirror in front of the transducer so that any photons that go to it will be reflected back out instead of going into the transducer and producing a signal. But if you look at this baseline, and there are ways to get rid of much of this baseline, nonetheless, I'm looking at this peak and I'm looking at this peak. This peak is due to the fact that there's an absorber there. This peak is just purely due to the excitation, the agitation of the transducer. So the baseline makes a big difference. So that's one of the things that you have to account for the baseline. And guess what? If you change the geometry, you change the surroundings of the signal generation process, this baseline is going to change. So you cannot normalize it out. Mostly what people do, they do high pass filtering. That is, they take all of the very sharp edges, they pass them through a filter so the baseline becomes a bit more smooth, but you still have some of the issues remaining. So the photoacoustic radar or sonar, what is it? So it is a method to generate acoustic waves by optical radiation, and you put a specific modulation pattern. Again, as I said, you're using coherent detection, that is, because you have waves that you control externally, these waves have phases, so it puts all the phases together so it can generate a peak. That's called pulse compression, and that achieves essentially high axial resolution. The reason for that is, of course, because once you have a pulse, you can separate this pulse from the next one. What changes or improves the spatial resolution is how sharp is that pulse. So what is the full width at half maximum? If it is small, then you have high axial resolution. What does the full width at half maximum depend? It depends on the total spectrum of frequencies that you put in there. This time domain and frequency domain are Fourier transforms of each other. So those of you who have taken a course or have had Fourier series or Fourier integrals or just Fourier theory, you appreciate that what is wide in one domain, it's narrow in the other. So if the pulse is quite wide, that means that the frequency spectrum is very narrow. But on the other hand, if you can have the opposite is true. You can introduce a large number of frequencies, so have a wide spectrum, then the pulse is narrow. The limit of that is a delta function. It's a Dirac delta function. Dirac delta function has an infinity of frequencies, and it is just a spike. It has zero line width. So that basically is not achievable, but this is the idea. So, and the other one is, once I have signal compression, and as I said, the other component here is going to be monitoring the filtering that, because that's a very noisy pulse. This is still a small amount of energy. You need to do filtering. So that filtering is extremely important. That has to go here, but once you have that, then you can end up with things like multi-element, ultrasound, sensor arrays, and so on. What we discussed in the morning is very similar to that. You can have single transducers, single sensors, multi-sensors, phased arrays, all these kinds of things that go into one kind of photoacoustics that go into the other as well. So we take advantage of the fact that we have essentially a radar here. So this was the idea of a radar. And it sends out a multi-frequency waveform that's called a chirp. Now that chirp, if you listen to a bird sings, and then if you have a frequency analyzer and you listen to that, you see it's essentially a chirp. It has multi-frequencies in it. And when those frequencies go together, and in your ear it sounds like a chirp. Actually, birds chirp, right? It's a chirping bird. That means it has a good frequency spectrum. It could be used as a good chirp generator. So the match filter signal compression is very important because, again, it gives you a high signal to noise ratio, so you get the peak. So a primordial for acoustic experiment for that is to have a CW laser that has gone into an absorber below the surface to generate thermoelastic expansion. It has to be fast enough so that you do not get heat diffusing out to distort your image, and then eventually you pick it up through an ultrasonic transducer. Our experiment, our goals have been, first of all, to generate the technology, and second, to apply it to things like breast imaging, breast cancer imaging. Once you have this kind of a scenario, you're really looking at a few centimeters below the surface. So we have not been interested in the high frequency range. We're really looking at essentially 1 megahertz to 5 megahertz. As we heard in the morning, the higher the frequency, the higher the damping of the acoustic waves. Ultrasound dampens, so the dampening depends on frequency. So low frequencies propagate quite a lot in the sample. High frequencies, less. And so if you go to ultra high frequencies like 100 kilohertz or like 1 megahertz or so, 1 gigahertz, then you can end up with millimeter. You can end up essentially sub-millimeter, a few microns. You end up with microscopy. But we're not at that end. We are at the far end. So we want to be able to penetrate deep to see the very beginning of a tumor that will be generated under a certain surface, a certain tissue that is scattering a few centimeters below. So in terms of the photoacoustic signal, well, we saw the time-honored equation in the morning, the time domain, time-honored equation. Now go to the frequency domain. What you do is you take that equation that Matt presented you with in the morning, you take the Fourier transform of that, and then you end up with this kind of equation here. This is the pressure. This is the Fourier transform of the pressure field that you generated. This is the wave number, the angular wave number of the pressure field, 2 pi over lambda. And then you have the right-hand side, and where you have the DDT became I omega here, and this is the Fourier transform of the source. So what does this pressure wave look like? What is it made of? Well, it's made, first of all, of the three things. One of them is the photoacoustic effect. I converted light to heat and to sound. So that is a component that goes right here. So I see this formula here. I'll get to that in a second. The second one is the modulation spectrum. However you modulate the light, you're going to get an acoustic signal out that is going to be a replica of that modulation. So this goes into that spectrum, and that has a frequency dependence. And then you go into the spatial light distribution. There's no frequency dependence here because light goes instantaneously as far as we go in this field. So that gives you essentially what the neighborhood is going to look like, what the illumination of the neighborhood is going to look like. Now, when you look at this formula here, you end up eventually saying as the frequency goes up, this goes like 1 over omega. There's omega here, there's omega squared. Omega is the angular frequency, the angular modulation frequency. That says that for acoustics is a low-pass filter, as far as you know. That is, at high frequencies, the signal is attenuated. So, that has an inherent advantage in the frequency domain because I don't really need a picosecond and a nanosecond laser that has essentially 1 gigahertz bandwidth if my transducer is only as good as about 1 or 2 megahertz or 5 megahertz. Everything else is going to be attenuated below that. So I'm not taking full advantage of the transducer. If I am to look at deep phenomena, then I don't need, essentially, those high frequencies. They're going to be attenuated anyway. So frequency domain gives you the advantage to work around frequencies that would optimize the response of the transducer. This is one of the major advantages. So then we see again very similar effects that we already know since we've been talking about it for the past 5 hours. That is, there is a absorption of the light, thermoelastic expansion, and eventually there's a transducer here picking up the signal. Now, if you are to implement that into a radar kind of approach, you can have 2 different ways of approaching that. I just simply point out some of how the signal formulation goes. I can have essentially a reference chirp. That's the chirp that will modulate the laser. So you really need to modulate your laser. And then you can go directly, which is somewhat's called in phase, or you can incur a 90-degree phase shift. And to incur a 90-degree phase shift, you have to make use of something that's called the Hilbert transform that actually delays part of the light, splits off and delays part of that of the signal that goes into the laser so that you can get 0 degrees and 90 degrees off. And that is going to give you the quadrature. Just like every wave. Every wave has an amplitude and a phase. It has an in phase and a quadrature. So I have a vector out here, there's the in phase, there's a quadrature, and if you go again into polar coordinates, you have an amplitude and a phase. So the in phase is this, and the quadrature is that. Now, the signals are going to be very low. So you need to do the, as I said, you need to do the filtering, the match filtering. So from communications theory, what you find out is, first of all, you do mixing. You mix the reference chirp with this chirp, this signal that comes in from the response of the material, which is very low and very noisy. They have to be mixed together so that one of them recognizes, hey, that part of the signal is noise. It's not really relevant to me, but that part is generated by my frequencies that I put in there. So this is a good part. How do you do that? You mix them. You multiply them. And then you use essentially a filter. But in this particular case, in a digital correlation processor with quadrature demodulation, that basically gives you the mixing, and eventually once you mix, you have a weighting factor that is pretty much like you do apodization. You get rid of some of the extraneous parts of the signal to clean it up a little bit. And finally, you do the in phase and quadrature. That is, you end up with 2 signals, in phase quadrature or amplitude and phase. These are essentially the case, but mind you, once you do this mixing is in the time domain. So this time domain mixing results in integrals. Integrals are slow when you do an integration. So in order to speed things up, you want to go into the Fourier transform of that. So you generate the Fourier domain cross-correlation signal processing. This is good, but it is too slow. This one is a fast kind of a signal. That is, I have two channels, a transducer and a reference chirp. I take my information out of the reference, and then here is the filter. Here is the key element of that. That is, the best filter to give you a huge signal-to-noise ratio advantage is the complex conjugate of a delayed version of the input waveform. That Z star that you see here, that has been proven to be the case with frequency domain experiments, or frequency domain theory in other fields, which is actually applicable here too. So this filter, that is the complex conjugate of a delayed version of the input waveform, is the one that gives you huge advantage and brings up the goodness of radar. That's why radars work in the first place. Otherwise, you'll never be able to get a strong enough pulse to get in there. So then the mixing and the band passing, which is again the shaping of the output waveform, but then now what you have done is, once you did this is a frequency domain here. So you have frequencies. And we all know from Fourier theory that in the time domain, what you have convolutions, that is integrals, these are products in the frequency domain. So it is much faster to multiply than to integrate. As a result, this is a very fast kind of a process. You do this, and you multiply, and eventually you take the inverse Fourier transform, and you end up with essentially a time domain. It's a time delay domain, but it still has an amplitude and a phase, because it was generated by two signals. This is radar theory. So I end up with an amplitude and a phase. And then what I have is the chirp goes in, so this is the multi-frequency wave. And I have a correlation processor, which is essentially, in this correlation, this cross-correlation, is only matching what comes out with what goes in, and it throws out everything else. So now you can have a high peak. You can actually move away from the noise. So this is the time domain aspect. This is the frequency, the Fourier transform of that. So you have the reference, the Fourier transform of the reference signal, the Fourier transform of your actual signal, and you're all set. Here is once again the transducer signal coming in, the reference chirp coming in, the match filter, the mixing, and eventually the output. So this is what you end up with. The theoretical form is this. You can have a sync function. Sync is sine x over x, essentially. So you have a peak, and these are the side bands of that sync function. And you have a correlation for a chirp 1 to 5 megahertz here. This is the function that you're looking at. And the most important thing is this one, this M, the time bandwidth product. That time bandwidth says, how long has the chirp lasted? The longer it lasts, the more energy it puts in, and so the stronger your signal-to-noise ratio is going to be. And how about the bandwidth? The higher the bandwidth that it covers, the narrower the half-width will have maximum here. Because you remember, it's the Fourier transform of ideally a delta function, but in reality it's not a delta because there's only so many frequencies you can put in there. So how small the half-width is here, and how good this time bandwidth product is giving information about the height and how far away you are from the noise. And if you do windowing, time windowing, this is several kinds of windows in communications theory that chop off parts of the spectrum, that if you put the windows right, then you get rid of some of the high frequency components that are these little hatched lines here, so you end up with a much cleaner signal, and importantly, with essentially a flat baseline. So this is what you have to compare against the baseline of the pulse laser that was going over that way. You have a clean baseline that you get away essentially from some of the artifacts that you get from the following the N-shaped pulse. Okay, so just to give you some ideas, and you can put all sorts of absorbers in there. Here's an absorber, a uniform absorber, so you end up with a match filter output, gives you two peaks, one as you enter here and one as you exit there. So the distance between the two peaks gives you information about how thick your absorber is going to be. You can also have all sorts of other absorbers. Here's an exponential distribution. So you can do this, you can figure out what the spatial profile of the absorber is going to be, because the relative size of these peaks changes as the absorption profile changes. Remember, what you do is, you pick it up, the first information is going to come in from the surface, because that's the acoustic wave that comes first. And then, as the acoustic waves are generated through the absorption of the light across the body of the absorber, the last one to come out is the one in the back surface, because that's going to take the longest time to come out. Time is on your side, as the Rolling Stones used to say. So, as a result, you wait long enough, and you pick up all of the acoustic waves coming to you from everywhere. And then you can actually reconstruct those. From this mathematics, all I wanted to show you is once you're in that, one of the advantages that you have with the frequency domain is you can do things like coherent averaging and incoherent averaging of the data. That is, you can put a match here, the match filter correlation is here, the ones that I mentioned before, and then you can put noise, you can put a Gaussian noise. Gaussian noise means all of the frequencies are in there, but there is some weighing, random, the noise is random, so there is, the profile of the noise is a Gaussian, something like this. So to just give you an idea, the incoherent averaging is post-processing. You pick up all of those signals that come back to you, you average them, and you end up with an average signal. But if you want to do better, then you do coherent averaging. The mathematics here is involved, but in reality it says coherent. You correct the phases. That's all it is really doing. Once you correct the phases, then things happen. And the way they happen is like this. When the coherent averaging counts is when the signal is low. So I have a coherent averaging of 100 chirps here. This sigma, which was the profile of the noise, is 100. The signal to noise ratio is minus 23 decibels. People who work with ultrasound, they'll know the decibel unit, which is the logarithmic unit. Logarithm to the base 10 of the intensity divided by some reference intensity. This is what your decibel is going to give you. It's a logarithmic unit because ultrasound has such a high range of signals. So linear responses are not the right thing to give. It's just too big for that. So you go into a logarithmic response. So you get orders of magnitude. And that's why you have a decibel scale. So this one is in minus 23 decibels because you have sigma at 100, but if the noise is more severe, then you get minus 25 decibels. So the signal is embedded in the noise as well. So you can see this here for coherent, it still stands strong and proud, but if you go to the coherent averaging, by the time you're down there, you cannot tell the difference between this peak and the surrounding peaks. Now, when you do this, it comes at a price. And the price is that you have to have a mighty computer to do the post-processing to adjust the phases of the signals that come back to you, so that's coherent averaging. So time in this case is on your side to get a higher signal, a higher output, but it's not on your side if you are to do fast imaging. However, we know how to do it. That's what coherent averaging does for you. So one of the things that we were doing was to compare signal-to-noise ratios and contrast between pulse laser and photoacoustic radar. So in this particular case, as we're developing the technique, we had essentially two lasers, a pulse laser and a CW laser, both of them at the same wavelength, and essentially brought them into a system, a very characteristic, very simple system that had an absorber below the surface of a fluid, and then we're picking up the information from a transducer, and we're looking at both the time domain and the frequency domain responses. How about the signal-to-noise ratios? Well, the time domain versus frequency domain signal-to-noise ratio, so the ratio of the signal-to-noise ratios is given by, it's proportional to essentially the intensity. This is the chirp bandwidth and duration, and then chirp bandwidth and duration, and the AI is the intensity of the pulse laser. So the signal output, the SNR output compared to the SNR input is given in the radar case by the duration of the chirp times the frequency bandwidth, which we call as an M here. So the right-hand side ratio, if you do this calculation for the frequency domain for the radar, you find out that it's the estimate gives you about 10 dB higher SNR for the pulse for the acoustic signal. So yes, we knew that already, but on the other hand, you know 6 orders of magnitude. By using the radar characteristics, you end up with a decent comparison. You're 10 dB away from the pulse laser. However, our experiments show that we have a much smaller difference between the two. And the reason for that we attribute to the fact that in the frequency domain modality, we tune the laser energy frequency spectrum within the transducer optimal bandwidth. So we move the frequency range toward the peak of the transducer range. Not exactly, because the peak of the transducer does not give you the peak of the photoacoustic signal. The point being that the photoacoustic signal is a low-pass filter, so you have to adjust that so that you can get the optimum out of that. And also, the pulse photoacoustic baseline gives you some kind of compromise because you have to make the baseline flat, and to do that you have to do high-pass filtering, and that high-pass filtering takes away part of the stamina of the pulse laser. So when you look at the safety limits, we discussed a lot about safety before. One of them is the signal-to-noise ratio for the ideal match filter is given by the square of the intensity of the laser that goes in times the chip duration divided by the noise spectral density. And then these are the curves that have been published. So different wavelengths, and they have different time scales and different wavelengths. They have different curves. So for near infrared wavelengths, such as those of the neodymium YAG laser that I presented to you before, you get some of these dependencies, how much the exposure time has to be. So here's the exposure time for a laser whose power is 1.76 watts. This is a CW laser, where you're really looking at the peak power. And here's one for 0.8 watts. So for 0.8 watts is a lower power, that means you can expose tissue for a longer time. On the other hand, if your power goes up, then the exposure of the tissue has to be shorter. Because otherwise, you don't want to fry it, you want to heal it. So you want to have the laser to be there without interacting with the tissue at all. And unless you are below that line, you cannot get FDA approval and other things that Matt was talking about in the morning if you eventually want to go into the hospital mode. Okay, so the power, if you're limited by the upper power, then it turns out that you can, if you wanted to go to a depth of about 3 centimeters below the surface with an effective absorption coefficient 1.5 inverse centimeters, which is characteristic of tissue, then you have to have an SNR output of about 16 dB. So it says that as long as I want to be below this line here, then I can see up to about 3 centimeters below the surface, which in this particular case is not too bad. Do you want to do better than that? Then you want to go to higher frequencies. If you go to higher frequencies, shorter time, less exposure, so you can up the power. But at this stage, we're still looking at the ability of laser technology to go up to maybe, 10 watts? 5 watts at a few megahertz, and that is still a challenge. Those lasers are not there yet. Also importantly, but the ones that we're talking about today, where you can get several kilohertz or so, the difficulty with those is that you cannot control them from the point of view of multi-frequency. You cannot introduce chirps. My ideal laser would be one that would be pulse lasers all the way, and then I can control the output through a chirp. That would be the ideal laser, but we're not there yet. Like that company is not there yet. But I'll check them out to see how good they're going to be. So here's some of the results of what I was talking about before. Resolution of contrast factors. This is the contrast factor is signal mean in the lesion, this is the absorber, minus the signal mean in the background, divided by signal mean in the background. So it gives me a relative change. So here is for this one is a delay time for a laser that has been introduced in the frequency domain. This one is cross-correlation of the amplitude. So I see essentially two peaks. One of the peaks is a reverberation of the surface. Laser goes in, the surface goes like that, so you get a pulse right from the surface. You always have that. You can time gate it. And then you also have the absorber below the surface that comes later. And you have some other junk here that comes in, which is not relevant. You want to get rid of it. So, but here's your amplitude. Here's the phase. So the key thing about it, this is the phase is one of the things that we find time and again, the phase is independent of the fluence. Why? Because phase is a ratio of two signals, a quadrature divided by an in phase. Both the quadrature and the in phase have the intensity of the laser multiplying them. The ratio of the two is independent of the intensity. So if you are to do any fluence independent kind of imaging, one of the simplest ways to do is use frequency domain for acoustic phases. That will get rid of much of that of the nuisance, I suppose, contribution or problems that you may have with fluence. It's not always 100%, but it is much better than the amplitudes. So then what we do with this, phase also, because depends essentially on interference patterns of different phases coming from different parts, it turns out that the phase has a higher spatial resolution than the amplitude. So where there is a signal, the phase immediately latches onto it. If there's no signal, then it goes haywire. If there's noise, you have problems with the noise, it goes haywire. So what happens is we discovered a method to use the phase along with the amplitude. That is, because the phase goes essentially from locked to unlocked, we take the inverse of the standard deviation of the phase. So when the standard deviation is very high away from the lock, the inverse of that is something divided by something very large, close to zero. At the time when the phase locks, then that gives you a finite number. So the inverse of the standard deviation of the phase gives you something that looks already much better than the amplitude. However, when you multiply the two, that's a bingo. That's where you want to be. The multiplication you do gives you the higher spatial resolution, and it also gives you essentially the depth of the baseline below. And now here is the CF factor for the pulse laser, granted without any high-pass filtering, but the difference between 264 and 5.9 is really quite a lot. So it says that your image here looks a lot cleaner than your image there. Sorry. Okay, so some of these results.
Is it time to take some questions?
Yeah.
So do we have some questions? Everybody following everything perfectly?
If we go back to, you have the comparison of two electronic diagrams for the chirp processing. And that looked to me a very, very sophisticated way.
This one here?
Yeah. So that's a lot of analogy which we have to use.
Well, yeah. The point is you have a waveform generator that goes into the laser, so it modulates the current, and then eventually the software is the one that picks up the information, and then it does all the multiplications and so on. So you really look at all of that is done in the computer, and the complex and this is also software, because you know what your input waveform looks like. You take the complex conjugate and you delay. So if there's nothing there coming to you, then there's the correlation gives you zero. You multiply something by zero, but then suddenly there is a signal coming in from some depth. Then you have the signal.
Because I still see the mixer, so I saw that you prefer to do it in the analog.
No, this one is coming, this is digital, it's all done digitally. No, yeah, we don't really use those. There's two mixers, in-phase and quadrature mixers. So we don't really use those. We try them in the beginning, but because they're slow, you can use an analog. We use analog mixers too. We use analog mixers. But this gave a much better solution. Yeah.
Could you explain the difference between coherent and incoherent detection again?
Yeah, incoherent, what comes into the system from the data acquisition board, it basically is co-added together. So you're adding things together and eventually you have a signal to noise ratio that essentially goes like square root of n. So the more signals you come in, the higher the signal to noise ratio, but there are phase differences between those signals. So you don't adjust for the phases. Coherent is when you just make adjustment. In other words, the clock that this gentleman was using in the morning was a really precise clock. So you adjust the phases to be just right, one time after the other, when they come into the data processing unit. That's what really brings a baseline down. Because if there's incoherence in the phase, then it essentially amounts like an effective signal. This phase does not cancel the other one out, so there's an effective signal there. So when you have the phases together, then they basically give you the true signal to noise, maximum signal to noise ratio. So in one case the baseline is up, in the other case the baseline goes down. But you pay a price, and the price is that you have to actually make sure that there is a software piece that adjusts the phases so they're just right for every cycle of the chirp, because you don't have a single chirp here. You may have 1,000 chirps. Each chirp, if you go from 1 megahertz to 5 megahertz, let's say, each chirp may last a few microseconds, but then you co-add about 1,000 of them together, so the whole duration is 1 millisecond. This is what you're really looking at. So all those, they just come in line like soldiers, like we're hearing. Okay. Any other questions, comments? Yes?
You compare the ultimate ratio. What about measurement time and processing time?
All of this, as I said before, measurement time, in order to be able to get 1,000 chirps, I need about 1 millisecond. So eventually, measurement time is reasonable. That is, because I have a high repetition rate, so I can get 1 kilohertz in there every 1 millisecond. So it's faster than the pulse laser for sure, the 10 hertz pulse laser.
What about your transducers? Because in optics, when we use, for example, 800 nanometers and a silicon detector, we give up 6 dB automatically because we only have a 25% quantum efficiency. How good is yours?
These are acoustic transducers, right?
Yeah, of course, yeah. But so is there an equivalent quantum efficiency?
Yeah, well, what you do is once you get your ultrasonic transducer, there is a transfer function that comes along with it. I think I'll talk about it a bit more. But you see, you have to adjust your spectrum, to do the waveform engineering properly, so you adjust it so it gives you a maximum within that transfer function. So the 3 dB, you take full advantage of the 3 dB down. Okay, so let's move then to this, which is like, here is a pulse laser system. We have at the depth equal the absorber 10 millimeters, 20 millimeters, and 25 millimeters. You observe the N-shaped waveform, so the waveform becomes smaller and smaller as you move further and further in, because this one was done in a solution, a scattering solution. It's called intralipid. I'm sure some people are aware of that. Basically, it simulates a scattering coefficient of tissue, and then 0.47% is where you have this simulation, which is closest to tissue. So you put the absorber deeper and deeper, and then you see those differences here. Those differences are due to the fact that from one pulse to the next, you don't really have the same exact repetition. So the pulses are strong, but because there are some shifts there in the way the transducer responds, and you get those high levels of essentially standard deviation. But the standard deviation is not that the noise level is too high, just like sometimes the signal is here, other times the signal is there. So you have to co-add all of the signals. Remember, the main advantage of the cross correlation is that the baseline is flat. This is one thing. So as you go deeper and deeper, you get a baseline to increase more and more. So now this is your response, but then if you do that, you have essentially at the far end, you have some large error bars, but they're smaller than the error bars that you saw before. However, again, you really get into about the same depth, about 25 millimeters away from the surface. So you get essentially an equivalence between the two. The cross-correlation amplitude, that is the delayed version of the incident waveform, multiplying the response, the photoacoustic response, either has an envelope, and it has an in phase and a quadrature, because it's a wave. So the in phase and the quadrature are there. Now you also have a phase. So the phase unwraps, and it changes, just the dramatic change. These are essentially, hundreds of degrees as you move out, the acoustic phase. But you have it there. So you get the inverse of the standard deviation of the phase, what I mentioned to you before. If I have an absorber, I lock. If there's no absorber, it goes out of lock. And by multiplying this two, the amplitude and the phase, then you end up with this clean wave. And this is again the surface, the response from the surface of the sample, which is reverberant. By the way, one of the problems with transducers is they are reverberant. They cause problems sometimes in the temporal response, but as far as the cross correlation is concerned, all of that stuff appears at time t equals 0. So there is a whole lot of here, it doesn't show here because it's cut off, but early on you can have a large amount due to the fact that one of these sources of that as I said, reverberant transducers. The other one is if there is, if you have things like radio frequency, RF, by the time you go to lasers that emit at 1 or 10 megahertz, then sometimes the semiconductor wires, they act like antennae, so you can have an RF coming in, and you want to chop off that RF. And that all happens at time t equals 0. So essentially, as long as you have some distance to go, you're clean away from the 0. These are some of the results that we started picking up from some absorbers. This is a black square rubber here in intralipid that simulates scattering tissue. This is the frequency domain amplitude 2 absorbers, a large one and a small one. This was a laser exposure 6.5 watts per centimeter square. This was a pulse laser. So what you find is these are very similar to each other. However, one of the disadvantages, because the pulse laser has a baseline that is harder to control, you find out an easier, so this one is a neater fit to the image. This is the neater image compared to this or that. And this was the frequency domain amplitude at 15.6 watts per centimeter square. So this one gives you essentially a better delineation of the absorber. And you can see those here too. This, keep in mind these sections A and B, I'm going to show them next time around. These ones are the large one, the large absorber, and the small absorber. So you have A, B, C, D. This is the pulse laser. So you have a very high axial resolution, because the pulse laser again is much narrower than the line width that you have. You only have so much frequency to play with. And then you have this section E and section F, and I'm going to show them what the sections are here. These are the sections. This is what you found with the pulse laser absorber, with the absorber of the pulse laser. So you have the two peaks here, and then these are the waves on the wake of the laser. Then the full width at half maximum 0.46 for this absorber. You get the cross correlation amplitude. You can see the difference between the front and the back of the absorbers. And then you have the inverse standard deviation of the phase, much higher, much better resolution. And here is now, in this particular case, the front and the back of this absorber, you see the multiplication of the amplitude and the inverse of the standard deviation of the phase, and I have a much cleaner resolution of the two waves. So I can tell where the front absorber is or where the back absorber is. So this is what I was showing you before. You can see, of course, you can separate them very nicely with the pulse laser, but you also have this other stuff that you have to interpret at times. And this is what the cross-section of the profile looks like. This is your pulse laser, and it has the additional information, which would be an artifact, and you have to make sure that you clean it out. If you put too strict a filter, then you take a high-pass filter and you take out part of the information. If you don't make it high enough, you don't make it strict enough, then it allows a lot of other waves to come in. So you have to strike a balance. When do you get the best filter to get the best image out of that? The cross-correlation amplitude and the amplitude filtered by the phase. So this is what I was telling you before. I see the two of them merging together. The actual resolution is not high enough because they have a finite amount of frequency range, but then by the time that I put the phase in there, then the resolution becomes better, and I can separate the two. This is the transfer function of the transducer. We were talking about the transducer effects before. Every transducer comes in with some transfer function that tells you this is the peak frequency. Our transducers are all in the low megahertz range because I want to be able to penetrate deep into the sample. So here is the case. And this is one transducer, this is another transducer. So look at one that's very low, below 1 megahertz, because that is also quite helpful in some applications. So, as I was saying before, there's no point in having very high frequencies because by the time you have 100 megahertz or so, this transducer is not going to be able to pick it up. So you might as well not have the very sharp source, the pulse laser, if you cannot do that. The only reason why you use the pulse laser is high signal-to-noise ratio, but you lose the high frequencies. And that's something that you do not want for very high penetration. We look at the transfer function, we looked at the model of a transfer function, Primholz, Lido, Mattei. This is an electric model for the transfer function of the transducer that has an amplitude and attenuation, and it gives you the information about the amplitude and the phase and of the transducer, or the real and the imaginary component, because this is part of your system. This is what your signal is going to look like. The transducer is going to add to that. And these are some of the responses of these transducers. You can get the magnitude, which is the black, with a peak here at about 3.5 megahertz, the red, which is the real part, and the blue, which is the imaginary part. So you can actually model the transducer that will be eventually taken out of the photoacoustic signal. So if you wanted to do true photoacoustic imaging, qualitative imaging, you want to be able to get rid of the transducer contributions. Otherwise, you'll be getting artifacts. And this is the photoacoustic wave generation. You got photoacoustic waves in 1D. These are 1D solutions. There's a scattering medium here. This is a model, and there's an absorbing medium below. So you can find a 1D solution, which is the signal decreases as a function of frequency. As I said, this is a low-pass filter. This is the low-pass filter right here for the photoacoustic signal. This is the coupling coefficient of the solid and the gas, or the liquid in this particular case. So this would be quite low. That's why we put the transducer and the sample in water. Or every time that you have an ultrasonogram, you put a gel. You couple the transducer to your tummy with a gel, because you have to have a high impedance. Otherwise, the signal is very low. Or you can actually have a 2D solution. Actually, as long as you have a Gaussian laser beam, that becomes a 2D axisymmetric solution, and because of degrees of freedom to the side, then you end up not with a monotonic response, but you end up essentially with an N-shaped kind of a response. Here is the effect of the photoacoustic component, low-pass filter. There is the real, the absolute, the amplitude, the real and imaginary part. This is the complex equation that you need. And finally, this is the grand total of everything. All of these components go together. That is, I have the transducer transfer function here. I have the absorption coefficient. As it increases, these curves increase. So you see the response is going up here. This is the response of the photoacoustic plus transducer plus acoustic attenuation. So all of these curves go together. Eventually, if you match them together, you get an optimum signal out. But that allows you, because you can play with the frequency spectrum of your system, you can maximize the signal by moving into the right range. And as you see, just by working at essentially at the center of the transducer response is not really the optimum, because the photoacoustic effect already is a low pass filter, so it tends to shift things lower. So what frequency bandwidth do I use? Again, you're looking at the case here, 0.5 to 3 megahertz. So this gives you the maximum. You would not know that, because you could go from 0.5, you could go to 1 to 3 megahertz, but then you get a lower response. Or you could go from 0.5 to 5 megahertz, so you think that you're better, but in fact you're worse off. Let alone the fact that if you increase the frequency response too much, then you have noise coming in, because noise does not care about frequencies. It comes in essentially at all frequencies. So the more open you are, the more noise you're going to get into the system. You really want to be as narrow as possible as far as noise goes. So there is a trade-off here. And the inverse of the phase, again, it's sharper than the amplitude, but it gives you, again, the same kind of idea. 0.5 to 3 megahertz in this case was the optimum. Oops. Let me just show you some of these waveforms. That is, you put in the spectrum of a laser chart. Now, this is essentially a straight line. This is the magnitude, so you can see all of these waves are coming in at the same level. And then you look at the response. This is the photoacoustic transfer function. This is the spectrum of the acoustic pressure. These are the low-pass filters. And then when you do the cross-correlation analysis, you end up with these two peaks right here, from the front and from the back of the absorber. So that allows you to do depth profilometry. These are some of the depth profiles that we got early on with this game. That is, we put an absorber here. There's a plastisulfandum and with a subsurface inclusion. There is a gap, an air gap here. So we did scanning, and you can see this is the time. So this is delay time. The shortest time is the one that comes from the surface. So you're always going to get that. That's a bottom image here, and then you have the surface of the absorber down there. But then there is a little chunk missing. Somebody took a bite out, and the reason for that is because there's an air gap right here. So that air gap does not allow the signal to go through, so it gives you a non-existent signal right there. So you can see the sequence in time. Interestingly, again, this comes to the point, why do I need phase? How does phase come into this? So this was an absorber that we put below the surface of in this solid, which was actually put a black ink in there, and there was a gel inclusion, a gel that simulates tissue. So you get an amplitude only from the location of the absorber, and then you get, once you have this absorber here, and then you go further down, this is a 39 microseconds. At 66 microseconds now, the waves are coming in from below, but the amount of light that went to that underlayer is not as much up here because you have a black absorber on top. So not exactly 100% black, but fewer photons are able to go through. So those photons generate a smaller signal. So you're always going to see the line here. But the phase doesn't show that, because the phase is the locus of the generation of the light. The phase does not care how many photons are out there. If one photon is good enough to give you a signal, you're going to get the same phase for 1 photon, 10 photons, 1,000 photons. All of these are going to give you the same phase, because the phase is always concerned about the delay time, and it's always the same delay time. So the phase doesn't care about the overlayer. So doing phase imaging allows you, essentially, would allow you, if this was, let's say, a photoacoustic imaging image of a disease or something to that effect, then the person who's looking at it, they might know that this is an overlayer, because you have the amplitude that shows this, but the phase doesn't. So it kind of separates out the fluence aspect. So fluence comes into play again. Phase is much more immune to fluence than amplitude. That's an advantage. We've done things like nonlinear chirps, just to show there's a linear chirp here. These are nonlinear chirps. You see, one of the things is, because it's a low pass filter, you can enhance the low frequencies to give you a higher signal. So that gives you some good results. Here is a case where you can do a waveform, this low frequency waveform. So you go way up here, you get also the phase corresponding to that. The difficulty with this is it gives you a good signal to noise ratio, but it tends to be more broadened, so you start losing some of your resolution. These are some of the results. We had these absorbers here, and so you see what happens to the amplitude images introduced with a linear waveform and a non-linear waveform. Then you go into the delay times for the linear and the non-linear, so it starts getting sharper, and then you go, whoops, sorry, this was the amplitude filtered by the phase images. So it becomes sharper, but certainly the non-linear has some advantages because of the signal strength, but has disadvantages because you start losing the resolution. Things happen as you expect them to happen. That is, you get an experimental signal-to-noise ratio that rises with laser intensity. So what we do here is we can optimize the chirp parameters so that you can get the best out of your experiment. One of the things that you can do is what kind of waveforms you introduce. You can introduce linear sine chirps like this. You can introduce square waves. The square wave, you can see the square here up there, and you can see the sine wave, and then you can see a pulse rate. The square wave is always higher because it has more energy under it than the sine wave. So you end up with a higher signal than the sine wave. And the correlation signal gain for square versus sine is about 5 dB. And you can see that these are actually theory and experiment, that they agree very nicely with each other. You can introduce other codes. There are codes called Barker codes. And some of the early work that Mann was doing was with Barker codes. And the thing about Barker coding is you have those side lobes in ultrasonics, so you want to minimize side lobes. And these codes are helping you in keeping those codes minimum, those side lobes minimum, and therefore the peak power coming out much stronger against higher resolution against the background. So we tried those as well. They work to some extent. The difficulty with the codes is that there are not very many codes that are known. This is a 13-bit 1 megahertz Barker code. This is a linear chirp, not the best. This one is a 13-bit, and this one is a 51-bit. So this one is not much improvement over that, maybe a little bit over the baseline, but the important difficulty here is that there are not very many of these codes that are known, so one has to be able to produce this code. So you're limited by the width of the code. So how did we implement this? We implemented this system in imaging just by putting absorbers in a scattering medium. Again, that wiping, that window wiping effect that Matt was talking about this morning is clearly here. So we have a phased array. That means like you're adjusting the array to pick up information from different locations, or to actually move the beam, to do beam steering into the medium. We have chicken breast and some absorbers below, and there was a tissue phantom here. These are two different things with an absorber below the surface and an inclusion. Ultrasonic waves are not going to give you that information if the mechanical properties of the absorber and the surrounding are the same, because you don't have the interface, you don't have the reflection. The reflection will depend again on the density and the speed of sound. As long as the two of them are very close to each other, you're not going to get that. But for acoustics, is going to give you exactly what you want. It is going to give you information because there's an absorber there. Yes?
And if you apply the technique for the skin, are you able to see the melanin granules?
Well, it depends on if the melanin is on the skin.
Yes.
You should be able to see that. Yes, people have done this work. This frequency domain spectrum, whatever you see in regular absorption spectroscopy, you should be able to see that too. As long as the melanin is absorbing more, we should be able to see it locally.
But what I want to ask really, so when you do that images, so and when something absorbs the light, it's presumed that it changes the temperature as well. Right?
Yeah, but it's not very high. The temperature doesn't, I mean, unless you're really zapping it to death, so that you're heating it more than you should. But remember, you have an upper limit, and it's true, if you have melanin, this is made for regularly absorbing tissue, but if you have melanin, or if you have, let's say, skin cancer cells, that they absorb more. So maybe you want to be more careful, but on the other hand, maybe if you adjust your signal baseline to conform to healthy tissue, just by having a few local absorbers, that's good, because you can tell that the absorbers are there. And importantly, even though you're talking about skin, it's not just skin, there is a subsurface to that. The absorber is not just sitting at zero thickness on the skin. So again, your amplitude and the phase is going to be able to penetrate that.
But if it's skin and melanin is shallow, how the spectral domain would compare in terms of axial resolution?
You have to have the right wavelength, the right acoustic wavelength. But the reality is the amplitude itself is going to see, the phase may not be there, because if it is too shallow, so that the wavelength is too long compared to this thickness, you may not be able to see. But the amplitude doesn't care. The amplitude is going to show you, I mean, you can actually take a piece of graphite and put it on your hand, and you can shine the laser on it, you're going to see a rise in the amplitude. So surface absorbers, the amplitude goes for. Phase does not care so much about phase absorbers, surface absorbers. But if there is any depth and the wavelength is commensurate, you should be able to see some phase shift. So these are the transducer arrays. The light goes in, and then you pick up the information from the transducer array. This is a phased array, so as was explained in the morning, and I don't really need to say that anymore, that is, you pick up information from different parts of the absorber, because simply this wave takes a longer time to get to the transducer than this wave, so you have to do dynamic beam focusing and steering, so that all of these waves are going to come in time. You see, all of them are formed together, so eventually they're going to come together here. So you can enforce the absorption that comes in from the medium. So all of that, all these transducer array issues are there. There is no difference here. The thing again was to look at, we had a dual mode for acoustic imaging to begin with, and pulse laser and CW laser. This is a transducer, it's a 64 element transducer. This is the intralipid white material scatterer, and the absorber is inside. This is the ultrasonic image, so you go in again, like that's what the radar does, it scans like this. And because this is a radar, it also scans. So we have a surface that always produces acoustic wave, and there is a suspected tumor below the surface. You see here the skin surface, the tumor vasculature is below, you see it clearly in this rat thigh. With the ultrasound, you don't know. You know that there's something there, but you don't really see the tumor. And this is ultimately the blood of the tumor, the angiogenesis of the tumor is generating these signals here. Important aspects, the point spread function. This is what David Boyce was talking about yesterday. Because this is a scattering field, you want to know at different depths, what does the point spread function look like? This is the conventional ultrasound image. This is not a real point, but it starts spreading. Even today's most sophisticated ultrasonic machines, they still have some spread. You can never get a perfect spherical response from a wire. So we put a wire there that has a circular diameter, and then you can look at the ultrasound and you can look at the photoacoustic response, and this is not bad. One of the things that you find is once you're doing this kind of imaging work, you get a bit of a stretch of the signal along the x-axis, and then you have to do signal processing and in order to be able to bring it back to something that's more shapely. The ultrasound is here, doesn't see anything, but the photoacoustic sees the absorber below the surface. And here I have, this is now the point where we say the wiper. So the wiper goes in and starts seeing the absorber below the surface. And here is, this was an immunodeficient rat. That means that we're growing the cancer on the rat as a function of time, the day 4 and then day 11. So on day 11, this has progressed a bit more, and you can see some of the different locations where the tumor is. So the thing is going back and forth, so you can use it as a radar, which it is. The other thing that we did was look at somebody had a signal taken from the arteries below the wrist. These are very near the surface, so it's not fair to, it's good. You know that now you have real blood, you have a human there, and you're looking at the arteries of the blood vessels of the human wrist, so you can clearly see them below the surface. How deep can I go? Well, we have been able to detect optical contrast down to 25 millimeters. So this is a good one. And mind you, 25 millimeters, you still have some ways to go. So this was not really the limit. You see the signal decreases quite a lot, but there's still a signal down there. And the reason for that is because this cross-correlation function is quite potent along with the filter. So the filter and the cross-correlation function is very good, and it gives you a good response. So I'm going to conclude this part. I'm going to have a break, and then we'll be back. I'm going to conclude this part by saying that what I introduced in part 1 is frequency domain for acoustic detection with linear frequency sweep laser source modulation and coherent detection for acoustic radar or sonar. The time bandwidth product increases the signal-to-noise ratio to within 10 dB of the pulse laser system. So in practice, this can be higher if you do frequency bandwidth tuning and cross-correlation baseline interference elimination. I'm going to present on the second part some of the applications of this. We combine the amplitude of the response with the inverse of the standard deviation of the phase, and we can get a contrast that is superior to the pulse laser for acoustics because we kill the baseline essentially quite well. The radar can exhibit similar lateral spatial resolution over the pulse PA. The lateral spatial resolution basically also depends on what kind of wavelengths you use, how high frequency you use. In this particular case, we found that for our purposes, for the deep penetration, where we use low frequencies, we can do just as well with the both systems. In other words, you don't take the advantage of the high frequencies that give you sharper edges that the pulse systems can do. We don't do that. We don't do microscopy. We're interested in going deep into the sample, below the surface of the tissue. You can use phase array. We have used phase arrays. We use it with ex vivo animals and human arteries, and it responds quite well. Now, one of the key advantages of doing this is because it has the potential to build portable and economical systems. As I said to you before, I can have an ultrasonic imager here that's commercial. It exists and it's being used, and I can put a photoacoustic system on top of that, piggyback on that, with small laser diodes that can enhance can be part of the system itself. So in some ways you get two for the price of one, or maybe you can charge 1.5 times and get the two modalities together, the ultrasound and the photoacoustic modality. And we can do, if you do that, then you can end up with image co-registration. You get the ultrasonic signal, and on top of that, you actually put the photoacoustic signal as well. So I'm going to leave it here for now. I'm going to take a break. Be back.
What's on our schedule now? Is this a coffee break or a regular break?
No, let's not have a coffee now, because I have the second part, which is applications that I'm going to do it photothermal. So just breaking between the two fields, for acoustic and photothermal, maybe the right time for a coffee. Now it's just a bio break, as we said, 10 minutes, and then go back.
Okay.
Let's take a coffee break.
So what do I do? Do I stop here? 10 minutes. Do I stop the...
Yeah, save.
Save?
Yeah, save.
Okay.
It will create a larger file.
It's going to create a file in the computer.
Yes, it could be that it is also directly saving it into the slides. So I think that it's only from the slides in the memory stick if you want to copy this right away and save it. But it keeps your slides intact.
So what do I do? I take this.
When you can copy this over onto the memory stick, and you can drop it in the room, or you can also drop it in your folder if you want.
Well,
why not? There's nothing in there. So
I prepared an extra for you.
Very good.
So it looks like as if it has saved the voice over in the same file. So in case you can probably open the file and just disable the voice over, and then it will remove this probably again.
Okay.
While with the others, it looked like you could save it in a different file, which didn't happen here. So.
Do you want this back? Or
I take then the second one. I leave it here on the table and we can.
Right. Yeah, you can trim the signal. So